In today's video, we're going to look at some additional factoring patterns that we can use. There's actually 4 patterns we're going to see today. One is perfect square trinomials, which is just a special case of the factoring we looked at last time. We have difference of squares, which is the subtraction of 2 terms. It's actually a binomial, where each term is actually a perfect square. So we might have difference between 4x squared and 9. Both of which I can square an expression. So 4x squared is really 2x all squared, or 9 is really 3 squared. And then we're also going to look at a pattern, either the sum or the difference of perfect cubes. So again, things that we can multiply by themselves 3 times, and then that pops up in our final solution. So let's look at these patterns. And again, our first pattern to look at is perfect square trinomials. Again, this is kind of a special case. Technically, you don't need to know any special factoring for this, but it's a nice pattern to look for just to save yourself some time if you see these kind of arrangements happening. So our first problem is to factor 4x squared plus 12x plus 9. And you might notice, again, the first term is 4x squared. Again, perfect square. To multiply that, I can do 2x times 2x to make 4x squared. And to multiply to get the 9, I can multiply 3 times 3. So let's see what happens if we put those into a set of factors. So we would have, 2x and 2x, which multiply to make that first term. And then we have 3 and 3, which multiply to make the second term, or the last term rather. And so if I check my multiplications, again, my inside values multiply to make a 6x. My outside terms also multiply to make a 6x, which would come together to make that 12x, positive 12x in the middle. All I need to do is make sure I have positives in both of my factors. But I have exactly the same factor. And that's why we call this a perfect square trinomial, because it is perfectly squaring the expression 2x plus 3 to get, if we multiply that out, 4x squared plus 12x plus 9. And so we can do the same thing with example 2. Again, notice your first term, 16x squared. That's a perfect square. I could do 4x times 4x to multiply to make that first term. To make our last term y squared, I could multiply y times y. And again, check these out to see what would make that middle term if we're on the right track. And so my inside terms would give me a 4xy, and so would my outside terms, 4xy. But the middle term on this one that we're looking for is a negative 8xy. So to make that happen, we need to have negatives on both of our y's. So again, still a perfect square trinomial. We could write this at 4 or as 4x minus y all squared. And that's just a more condensed version of writing out my factors. And again, this is just a pattern that you might see. This doesn't need to be something special for you to remember. It's just a nice, neat pattern that you might start seeing in some problems. But you can always go back to your regular factoring trinomials techniques that we looked at in the previous 2 lessons. Okay, our next example that we're going to look at is difference of squares. And the name of the pattern tells us exactly what we're looking for. We're looking for 2 terms that are perfect squares, and we're going to have a difference between them. So first example is n squared minus 64. And again, both of those are perfect squares. So I can perfectly square an n to make n squared, and I can perfectly square 8 to make a 64. But the kicker is we need to be able to multiply this back together again and actually only end up with 2 terms. So let's think about what we would need to do. We basically need to cancel out that middle term. We want a middle term of 0. So how could we make 0 out of 8 and 8? Well, if one was positive and one was negative, then when we multiply these back together again, and let me actually use a color coding here. We have a positive 8n from our middle terms. We have a negative 8n from our outside terms, and those would cancel out, and all we would be left with is the n squared from multiplying the first 2 and negative 64 from multiplying the second 2. So our final answer ends up being n plus 8, n minus 8. And again, it doesn't really matter what order we write these factors in, as long as we have one that's n plus 8 and one that's n minus 8 in any order. Alrighty. Example 4. So in example 4, we are going to factor 25a squared minus 36x squared. Again, both are perfect squares. So you always want to think about, well, what can I multiply by itself to make each term? So on this one, we can multiply to make our 25a squared, 5a times 5a. To make a 36x squared, well, what do you multiply to make 36? 6 times 6. What do you multiply to make an x squared? X times x. Then again, to make sure that our middle term cancels out, if we were to multiply these back together again, we would have one positive and one negative. And that is all there is to that pattern. So why do I have these extra expressions for examples 5 and 6? Well, sometimes when we go through and factor, we actually might find one of these patterns hidden in another factoring problem. So let's check out example 5, which has 4 terms to it. So the first thing that I think whenever I see 4 terms, and actually even before I see the first 4 terms, what should I look for every single time I factor any expression? We should always look for a GCF first. So out of all 4 of these terms in example 5, it looks like I could divide out a 4 and an x from every single term. So let's write that out first. So we would have 4x times, we'd have a leftover x cubed from the first term, a positive 2x squared from the second, a negative x from the third, and a negative 2 from the fourth term. Now from here, I still want to use my factoring technique. So now I see I still have these 4 terms. So what was the only technique that we've done so far that used or that factored out 4 term expressions? Factor by grouping. So if I group my first 2 and my last 2, again, my first 2 have in common an x squared, which leaves me with an x plus 2 when that's factored out. I have a negative in the middle, and I always want to go with that same sign when I'm doing my second group. But that's the only thing that my second group has in common. So technically, I could think of this as I'm factoring out a negative 1, and that would leave me with x plus 2, which matches with my first group, which I always want to make sure that that's happening. Alrighty, so we had x plus 2 in common. We had a leftover of x minus 1. I'm going to go ahead and copy down my 4x that we did in the first step. We don't want to lose that GCF. It's still part of our final solution. But now I'm noticing I've got x squared minus 1. And this is why I brought this example up, because x squared minus 1, wait a second, x squared is a perfect square. 1 is a perfect square, 1 times 1. So I could use my difference of squares pattern on this and factor it out even further. So my x squared minus 1 can actually factor out to x plus 1, x minus 1. And again, doesn't matter what order I write my factors in. And I'm just going to copy down my x plus 2 and my 4x. And that's my final answer. Now, you probably won't see too many of these, but they can absolutely happen. So again, don't forget, we looked for a GCF first, and then notice that we had a 4-term polynomial. So that means we could do factor by grouping. And then it had that hidden difference of squares in there. What about example 6? So looks a little bit more simple for example 6. But again, I've got some extra pieces. If I look at them just by themselves, x to the 5th, well, he's not a perfect square by himself. 9xy, again, not a perfect square by itself. So I want to fall back to what's the first step I should do on every single factoring problem? Well, let's go through and see, do we have a GCF from x to the 5th, 5, and 9xy? Well, both of them, I could take out an x and a y. Now, granted, there's more x's. I have x to the 5th in that first term, but the maximum number of x's in that second term is only an x. So my GCF is x, y. So if I factor that out, I'm going to be left with x to the 4 minus 9. Now, if you think perfect squares, you're going to be thinking, hey, raised to the second exponent. But don't forget, any even number, if you go back to basic exponent rules that you've learned before, any even value I can really think of as a perfect square. So really, kind of as a side note, don't forget x to the fourth is really x squared times x squared. If I saw x to the sixth, well, that's really x cubed times x cubed. Our rule was for exponents, all you do is add the exponents if you're multiplying your monomial. So let's factor them out. So again, if we've got a difference of perfect squares and I know x to the 4, well, I can multiply him or multiply to get that by doing x squared times x squared. That's my first term in each factor. And then we have 9. Well, he's a perfect square 3 times 3. One factor has to be positive, one factor has to be negative, and then I just copy down my GCF that I had from the first step. Alrighty, go ahead, pause the video if you need to take a break. I know it's a lot of problems in a short amount of time. Okay, let's look at our last pattern now. So this pattern is called sum or difference of cubes. And I like to keep these patterns together because they're really the same pattern in disguise. The only change is what order your signs are in. So your terms themselves are always going to have the same pattern. Now, when we're looking at these, it's always going to be a binomial, 2 terms. And to use this factoring pattern, they both have to be perfect cubes. So just like we thought of before, let me shrink my screen down a little bit. Just like we thought of before, perfect cubes could be, for example, x cubed, which is really x times x times x. Actually, I don't need to shrink that down. 216, and this is one thing that you might start recognizing the more of these values you work with, is actually 6 times 6 times 6. Some of the perfect cubes that you might want to try to remember would be, well, 1 cubed is still just 1. 2 cubed, or 2 times 2 times 2, is 8. 3 cubed would be 27. 4 cubed would be 64. 5 cubed is 125. And the only reason I can rattle these off is I've seen a lot of factoring problems where I'd have to double check these. Don't forget, you could do this on a calculator as well. So look for a cube root option on your calculator if you need to check your perfect cubes. And so our last example with those perfect cubes, 8x cubed y to the 6. And again, just like we said, well, y cubed times y cubed would make y to the 6. Is there a way we could break this up into 3 pieces? Well, what's 6 divided by 3? So in essence, we're looking at 2xy squared times 2xy squared times 2xy squared. So that expression is still a perfect cube. We just need to think about how the individual kind of factors in their work. So our 2 patterns that we have, sum of cubes pattern and difference of cubes pattern. So I always think about the signs last. So if I know I have these perfect cubes, a cubed and b cubed, then the first factor in my final answer is going to have those perfect cube roots. So whatever I had to multiply to make a cubed, or whatever I had to multiply b cubed, or whatever was in those spots. Then our second piece is actually a trinomial, and this will never be factorable. It will never work out. We will take our a term and square it, multiply the a and the b term, and then square the b term. And this is exactly the same pattern in difference of cubes. So a, b, a squared, ab, and b squared. The only difference comes from the signs. So if you're dealing with a sum of cubes, you're going to have a positive, a negative, and a positive. If you have difference of cubes, a cubed minus b cubed, you're going to have a negative, a positive, and a positive. The easiest way to remember these is the acronym SOAP. So SOAP stands for same, opposite, always positive. So we have the same sign, the opposite sign, and again, always positive compared to the sign that we started with. And it's the same thing in difference of cubes. So we started with a negative, we have the same sign, we have the opposite sign, and the last one is always positive. And so no matter whether you're dealing with sum of cubes or difference of cubes, the order of the terms and how you kind of fill those in are always the same, and then just follow your pattern for your signs. So let's try this out on a few different problems. So let's start pretty straightforward. X cubed plus 27. So when I'm doing this, I always like to figure out, well, what are the A and the B values? What are my perfect cube roots that I'm going to have to use for this? And so if I write those off to the side, that'll help me remember what's going on, or I could even just fill them into the pattern. And so I find that's actually the easiest way to get going. I always do that first set of parentheses first. So think about, well, what do I have to multiply by itself 3 times to make x cubed? Well, that's just x. What do I have to multiply 3 times to make 27? Well, that's my 3. And so those are my A and my B values. And that's how I'm going to do the rest of my pattern. I'm just going to fill those in. So again, I'm going to take whatever was in the A spot and I'm going to square it. So x squared. Take my A and my B values, or the first and the second term from that first set of parentheses, and just multiply them. So 3x. And then I square the B value to make the last term. And then my signs, I started with positive, so same, opposite, always positive. And it really is just a pattern to these problems. We don't have anything extra we need to do. This trinomial that we have is actually not factorable. You could try it out and you will never find a combination of factors that will work with that. And you might be thinking, well, how in the world did somebody figure out this pattern? Well, they actually saw this happening when they were multiplying factors together and saw that they always ended up having these terms canceled out. So again, if you don't believe me, let's go ahead and check our work just to make sure that this does indeed follow from the factors we created. So if I check this out, I'm going to want to take each term from my first set of parentheses and distribute it over everything else. So I'm going to take my x and distribute it over all 3 terms. So that would give me an x cubed minus 3x squared plus 9x. And then I'm going to do the same thing with the positive 3, distribute him over everything. So that would give me a negative 9x. Excuse me, I did this out of order. I have a 3x squared. Then, so 3 times x squared, 3 times negative 3 would give me a negative 9x. And then positive 3 times positive 9 would give me a 27. Except, wait a second. I have a negative 3x and a positive 3x, they cancel each other out. I have a positive 9x and a negative 9x, they cancel each other out. And all I'm left with in the end is the x cubed from the front end and the plus 27 from the back end. And that is exactly what we started with. So again, you're free to go through and check these every time, but as long as you're really careful about your pattern and taking your time in proofreading, you should be in good shape. So that means our final answer was this expression up here. All righty, let's try another one of these. So 8a to the 6 plus b cubed. So again, I always start with, what are my perfect cubes? So to get an 8, again, what do you multiply by itself 3 times? A 2. A to the 6, what do I multiply by itself? I can do a squared times a squared times a squared. And then b cubed is just b. So again, these are your perfect cube roots of both of those terms. So then use those to feed into the second piece. So I'm going to square my first item. So I'm going to write this out just so you can see the thought process. So that means I'm going to take 2a squared and square it. I'm going to multiply 2a squared times b. And then I'm going to just do b squared. Then I fill in my signs. Same sign, opposite sign, always positive. And then let's just simplify to make our final answer. Nothing else changes from that first group, but you always need to write that first group down. 2a squared times 2a squared would give us a 4a to the 4. Basically, we already have our middle term multiplied out. That's negative 2a squared b. And we have a b squared. Alrighty, there we go. Go ahead and pause the video and try out the next two examples. Okay, let's see how you did. Alrighty, 64x cubed plus y to the 6. So again, to make a 64, 4 times 4 times 4, we would need an x, and we would need a y squared. Square that first term. So 4x times 4x would give me a 16x squared. 4x times y squared is just 4xy squared. Y squared times y squared gives me y to the 4th. Same sign, opposite sign, always positive. Now, the only difference with number 10 is we're going to reverse those first two signs because we're starting with a subtraction. But it's really no different on the pattern. So starting out, 8x to the 9. So I know 2 times 2 times 2 gives me 8. What multiplied by itself 3 times would give us the 9? And your hint is, what's 9 divided by 3? Well, it's x cubed. 27, also a perfect cube. 3 times 3 times 3. So then we square the first term. So 2x cubed times 2x cubed, 4x to the 6. Multiply your two terms together. So 2x cubed times 3 would give me a 6x cubed. And then 3 squared would give me a 9. And then do your signs. We started negative, so it's same sign negative, opposite sign positive, last is always positive. And there's your final answer. Okay, 2 more problems. And again, example 11 is pretty straightforward. It's just a matter of figuring out what, wait a second, 250. I don't know that that's a perfect square necessarily. It's not one that I remember. So check out your other term as well. So 2x cubed. Is there something you can multiply by itself 3 times to make a 2? No, without looking at decimal values, we don't have anything. But what's our first rule of factoring? What should we always check for? Take a GCF out and see what happens. So this is really going to be equal to, if I take out that 2, I'm left with x cubed minus 125. And actually 125 is a perfect cube. It's 5 times 5 times 5. So I want to make sure to copy down my GCF. I can't forget about that. First term, x, because x times x times x gives you the x cubed. 5 times 5 times 5 gives you 125. And then use those for the rest of your pattern. Square the first term. Multiply for the middle. Square your last term. And then check your signs. Same sign, opposite sign, always positive. Alrighty, so our last problem is example 12. And we have 216m to the 9 minus 64w to the 6. Now, looking at these values, 216 I know is a perfect cube. I know 64 is also a perfect cube. So let's see what happens when we jump straight in. Although if anybody has any light bulbs going off on here, hold that thought, maybe pause on writing things down. Let's see what happens. So 216 I know is 6 cubed. M to the 9 is the same thing as m cubed times m cubed times n cubed. 64 is the same thing as 4 times 4 times 4. And w to the 6 is w squared, w squared, w squared. Wait a second. I have a 6 and a 4. And if my goal is to factor this out completely, I know I'm going to have to take an extra step because 6 and 4, don't they have a GCF? Yeah, so I'm thinking I should probably check for a GCF on this problem. So I'm going to stop this train of thought. And let's see what happens when we factor things out. So let's see, 64 I know is 8 times 8. So could I take an 8 out of 216? Well, let's see. So 216 divided by 8, that actually gives me 27. So let's see what happens when I write that out. So I have, if I take out an 8, I have a 27 m to the 9 minus 8w to the 6. 27 is still a perfect cube and 8 is still a perfect cube, but they're much smaller numbers to deal with. So let's proceed from there. So I'm going to keep copying down that 8. 27 is really 3 times 3 times 3. M to the 9, again, m cubed is my perfect cube root. 8, we're now down to a 2 as the perfect cube root, and w squared. Nice prime numbers that do not have any common factors. So let's use that to keep finishing up. So again, square the first term to make the first term in the trinomial. So that would give us a 9m to the 6. Multiply your two parts together, 6m cubed w squared. And then square the last one for the last term. And again, I'm going a little bit off the page, but hopefully you have enough room. We'll have a 4w to the 4th. And then check your signs. We started with negative, so same, opposite, always positive. Always double check that. If you get to any smaller steps and notice that you have something with a GCF, it's not a bad idea to back up to your first step, see if you can find that GCF and factor it out. If you leave your GCF in a factoring problem, you will not have it fully factored out. So always make sure if you have a GCF, factor it out in that first step. As always, let me know if you have any questions, and see you next time.